So we get that we were showing that the integral from minus infinity to infinity of f sigma x is less than equal to 1. So like they are integrable at by putting t equal to 0. This is easy to see, as if you take mods, phi of s is always less than or equal to 1, and exponential of minus s square by 2 sigma squared. This evaluates to square root of 2 pi by sigma, which is already in the denominator. So this will be less than equal to 1. Now from here, we observe that as we had made this observation earlier also, that f sigma x monotonically converges to f of x. These f sigma x are integrable. So we get by the monotone convergence theorem that f is also integrable. And in fact, the integral of f of x dx over minus infinity to infinity, it is integrable, is limit of integral of f sigma x as sigma goes to 0. We had calculated what f sigmas were. So this will give you that this is equal to sigma going to 0 limit integral minus infinity to infinity phi of s e to the exponential minus s squared by 2 sigma squared ds by square root of 2 pi sigma. Now we make a change of variable, which is we take s by sigma to be some t. So this will give you not s by sigma, yeah, s by sigma to be some t. This will give you integral minus infinity to infinity. S is t sigma, so this is t sigma. Yeah, 2 sigma. So ds by sigma will just become dt, and the exponential above will become some exponential in t squared by 2 dt by 2 pi. Yeah, this is what we want. So where by monotone convergence theorem, we can take the sigma inside. As we take the sigma inside, we'll get this is equal to integral phi of 0, as phi is continuous, exponential t square by 2 dt by square root 2 pi. We had taken phi of 0 to be 1, so this is equal to 1. Now, since we have shown this, it's easy to see that this quantity, we take the limit of this quantity as sigma goes to 0. This will be e to the itx of f of x. Now, what you do is, we had calculated this Fourier transform of f sigma, and we had gotten, I think, this expression. This is the expression we had. In this expression, what you do is, we use the change of variable. S is equal to some z plus t sigma. Yeah. No. We just take z to be t plus sigma x. Wait, let me just erase this. So what that will give you is, you'll get the quantity f of t plus sigma x here. this will become some exponential, and with the same logic, like we just had t in this case, what we just calculated here. In that case, we won't have t equal to 0, but we just shift it so that t will go away, and that will give you that this is equal to phi of t. To understand why t is coming here, in this case it was 0. In that case, when we make a shift of t, you'll get phi of t plus some sigma s. Yeah, you'll get phi of t plus sigma s, and that t will, because phi is continuous everywhere, that will result in this becoming phi of t. So we get our result that phi of t is the characteristic function of some random way, some probability distribution, where f of x is the density function. F of x was non-negative, and the integral of f of x over the whole real line was 1. So we have proved that phi of t is a characteristic function. For a general phi of t, which is not given to be integrable, we do the following. The idea is we'll construct certain characteristic functions labeled by sigma, which converges pointwise to phi of t, and we'll use the Levy's continuity theorem, and we'll state the Levy's continuity theorem also. So suppose phi of t is some given function, not necessarily absolutely integrable, but satisfying the conditions already given in the theorem. Then phi of t e to the I t y. This is also positive definite for all y. We had seen this, we had established this in the properties. Now consider this convex combination of now this is also positive definite. This is easy. This is actually very easy to see because we are integrating over dy. Phi of t can come out. This is just a convex combination of phi of t. And we had shown that if we have here, the positive definite functions are labeled by y. They are labeled by y. All these positive definite functions are, all these functions are positive definite. And so their convex combination by will also be positive definite. We had established this in. Now, again, doing what we did, we integrate this over y. We complete the square, change the variable from, so that, okay, we don't change the variable in this case, sorry. We complete the square in y, and we integrate this over real numbers. We'll get some Gaussian integral, and the Gaussian integral will be such that this for factor we have 1 over square root 2 pi sigma. The integral will come out to be that. So from that, we'll get that this is actually equal to e to the phi of t times exponential sigma squared t squared by 2. This is easy to see, like the same calculations. Now, what this gives you is phi of sigma t is phi of t exponential t square by 2. Observe that the right hand side is integrable because the modulus of that is less than equal to exponential of minus sigma square t square over 2, which is integrable. So we have phi of sigma t as absolutely integrable, positive definite function satisfying all the conditions given in the theorem. As we had established that any such absolutely integrable positive function is the characteristic function of some probability distribution, we get that phi sigma of t is a characteristic function for all sigma. Now observe that again, this as sigma goes to 0, this converges monotonically. By the way, we don't need monotone convergence. We just need convergence. So as sigma goes to 0, this converges, phi of sigma t converges pointwise to phi of t. So by Levy's continuity theorem, phi of t is a characteristic function. Characteristic function. We'll state the Levy's continuity theorem also. So suppose we have characteristic functions phi n t. We have a sequence of characteristic functions converging pointwise to phi of t, which is some function. Then phi of t is a characteristic function if and only if phi of t is characteristic function of some probability distribution if and only if phi of t is continuous. So we get that by Levy's continuity theorem that phi of t is a characteristic function. So we got the theorem. Thank you. Yeah, it's like, it'll take very long time. Okay, sir. Thank you.
Niranjan, any question?
Niranjan?
Are you there?